Hi boys and girls, this is lecture 5.8, the topic integration by substitution, and this is the second part of that discussion. As we saw in the previous lecture, with a formal change of variables, you can completely rewrite the integral in terms of u and du, or any other convenient variable. This may be helpful with more complicated integrands. We let u equal g of x and du equal g prime of x. This transforms the integrand from f of g of x g prime of x dx to something a little simpler to integrate, f of u du, which of course is the antiderivative f of u plus c. Now let's do an example using u substitution. First of all, let's rewrite the integrand as the quantity 2x minus 1 to the 1/2 power dx. Previously, we let the inner function be g of x. Now I'm just going to call it u. And then I would need to also find the du pieces in the integrand as well. The derivative of our function u is 2 dx. Here's dx, but 2 is not in the integrand. Fortunately, I'm able to multiply by a constant if I need to, so I can multiply the integrand by 2 as long as I compensate for multiplying by the reciprocal 1/2 on the outside of the integral. That means now 2 dx, which is du, is also a part of the integrand. So u is 2x minus 1, and du is 2 dx. Substituting these values into the integrand gives me 1/2 u to the 1/2 du. U substitution gives you a simpler form of the integrand to look at when you're determining how to integrate. I'm going to add 1 to 1/2, which gives me 3/2, and then I'll need to divide by that new exponent, which is the same thing as multiplying by the reciprocal. So the 1/2 is going to be now multiplied by 2/3 u to the 3/2, which gives me 1/3 u to the 3/2 plus c. In the final step, substitute the original quantity back in for u. 1/3 2x minus 1 to the 3/2 plus c is your answer. Occasionally, you will have an integral which cannot be evaluated with the given form of the integrand. In those cases, you will have to use u substitution to rewrite the integrand into a form which can be evaluated. Let's do an example like that. At first glance, we may think this is very similar to the previous example. If we let u be 2x minus 1, the inner function, then du would be 2 dx. Well, we do have the dx part here, and we don't have the 2, which is not a problem, because we would be able to multiply the integrand by 2 and compensate for it by multiplying the integral by 1/2 on the outside. But what is preventing us from doing this is the fact that there's an additional variable in the integrand, which is not part of the du. This means that we're going to have to do a complete overhaul of this integral in order to evaluate it. Let's see how this works. This is the integral x, 2x minus 1 to the 1/2 power dx. We will let u be 2x minus 1. Our strategy here is to start with this u substitution and then rewrite the entire integrand, replacing anything that is in terms of x with a value, with an expression that is in terms of u. So I'm going to need to not only replace the 2x minus 1, I'm also going to need to replace the x and the dx. So du would be 2 dx, but I can solve for dx here by dividing by 2. So this would be du over 2 equals dx, and that's the value that I'll replace for dx. So I have expressions with u to replace 2x minus 1 and dx, but I also need to replace the x. So let's go back to this expression and solve for x. U plus 1 is equal to 2x, which means x is equal to u plus 1 over 2. Now, let's rewrite the integral using our expressions in terms of u. X, of course, is u plus 1 over 2. And then 2x minus 1 is u, so this will be u to the 1/2. And then dx is du over 2. We'll write this as 1/2 du. Now I will be able to integrate with the integrand in this form. Let's do a little rearranging. First of all, I'll have the 1/2 multiplied by the 1/2 in this first term, and I'll bring that outside the integral, which will give me 1/4 u plus 1 times u to the 1/2 du. Now let's distribute the u to the 1/2 to both of the u terms. 1/4, then I'll have u to the 3/2 plus u to the 1/2, and then of course du. Now notice that I can integrate each of these terms using the power rule. So this is going to give me 1/4. Adding 1 to this exponent gives me 5/2, so this will be 2/5 u to the 5/2. Adding 1 to this exponent gives me 3/2, so I'll have 2/3 u to the 3/2, and then plus c. Let me distribute the 1/4 to each of those terms, and that's going to give me a 1/10 u to the 5/2 power plus 1/6 u to the 3/2 power plus c. And of course, for my final answer, I will substitute for u the original expression from the integrand, which is 2x minus 1. So I'll have 1/10 2x minus 1 to the 5/2 power plus 1/6 times 2x minus 1 to the 3/2 power plus c. And that takes u substitution to a whole new level of usefulness. No pun intended. Here we have another trigonometric integrand. In the previous example we saw like this, we were able to let u be the argument of the trigonometric function, but that's not going to work here. As we examine this integrand, this chain wreck, we can see that the main function was something raised to a power, and that power was probably a 3 if the derivative gave us an exponent of 2. Well, what was the inner function being raised to the third power? It was sine of 3x, which means we have to let u be sine of 3x. This means that du is equal to cosine of 3x times 3 dx. Now notice that we have the cosine 3x dx part of the du, but we don't have the 3. So we are going to have to manipulate this integral a little bit by multiplying by 3 on the inside of the integral and then by the reciprocal 1/3 on the outside. Now the 3 along with the cosine 3x dx is the du of this function. And if we rewrite the integral using our expressions in terms of u, we end up with 1/3 u squared du. To integrate, we'll add 1 to 2, which will give us an exponent of 3, and then dividing by that new exponent gives us 1/3 times 1/3 u to the 3rd power, which results in 1/9 u to the 3rd plus c. And of course, we substitute the original value back into our expression. We end up with 1/9 sine of 3x to the 3rd power plus c, which can also be rewritten this way: sine cubed 3x plus c. Now let's formalize the u substitution process by discussing guidelines for making a change of variables. Choose a substitution u equals g of x. G of x is usually the inner part of a composite function, such as a quantity raised to a power. Then compute du, which will be the derivative of the g of x function. Rewrite the integral in terms of the variable u and find the resulting integral in terms of u. Of course, once that's done, you replace u at the end by the original g of x function to obtain an antiderivative in terms of x, and then you can always check your answer by differentiating. Which brings us to the general power rule for integration, where perhaps the integrand is a function raised to a power rather than just the variable x. If g is a differentiable function of x, then g of x to the n, g prime of x dx, can be integrated in this way: g of x to the n plus 1 over n plus 1 plus c. Of course, as long as n is not equal to -1. Equivalently, if u is equal to g of x, then u to the n du can be integrated in this way: u to the n plus 1 over n plus 1 plus c. Let's do a few examples. In this first integrand, we'll let u be this inner function 3x minus 1. Du then will be 3 dx, which is handy because that's exactly what we have in the integrand. U is 3x minus 1, and du is 3 dx. Let's rewrite the integrand. We'll have u to the 4th du, which integrates in this way: 1/5 u to the 5th plus c. Now replace u with the original expression, and we have 1/5 3x minus 1 to the 5th plus c. Now let's look at the next integrand. This is the more complicated looking function, so let's see what happens if we let this be u. It turns out that the derivative of x squared plus x is 2x plus 1. So this piece with dx is our du. So that means u is x squared plus x. Du is 2x plus 1 dx. Rewriting the integral, we have u du. To integrate, we get 1/2 u squared plus c. And of course, we replace u now with the original expression: 1/2 x squared plus x, quantity squared plus c. In this last example, let's let u be the inner function inside this square root, x cubed minus 2. Du is 3x squared dx, which is exactly what we have. So that means u is x cubed minus 2, and du is 3x squared dx. Rewriting the integral, we have u to the 1/2 du. To integrate, we get 2/3 u to the 3/2 plus c, and of course, as our last step, we replace u with the original expression. So this becomes 2/3 x cubed minus 2 to the 3/2 plus c. Here are a couple more examples. Look at the first integrand. Let's rewrite this as -4x times the quantity 1 minus 2x squared to the -2 dx. Here we can then see that this is the inner function u, and our du will be -4x dx. So u is 1 minus 2x squared, and du will be -4x dx. So rewriting the integral in terms of u gives us u to the -2 du. Integrating gives me -u to the -1 plus c. But of course I'm going to replace u with the original expression. So this will be negative quantity 1 minus 2x squared to the -1 plus c, which can also be rewritten as -1 over 1 minus 2x squared plus c. In this last integral, notice we have a trigonometric integrand, and since we have a quantity that is raised to the second power, it stands to reason that the original function was something raised to the third power. What was that quantity? It was cosine x. So u has to be cosine x, and du has to be negative sine x dx. So we'll have u equals cosine x. Du is negative sine x dx. Now we do have sine x dx, but we don't have the negative. So we will have to compensate by multiplying by a -1, and of course multiplying by a negative on the outside to compensate for that manipulation of the constant. So now let's rewrite the integral in terms of u. This then becomes u squared negative from here, and then u squared du. The integral of this is -1/3 u cubed plus c. As always, our last step is replacing u with the original expression. This will give us -1/3 cosine x cubed plus c, which can also be written in this way: -1/3 cosine cubed x plus c. In our last example, we're going to demonstrate using a change of variables for definite integrals. When using u substitution with a definite integral, it is often convenient to determine the limits of integration for the variable u, rather than to convert the antiderivative back to the variable x and evaluate at the original limits. Let's see how this works. In this integrand, here's the inner function, so we're going to let that be u. So if u is x squared plus 1, then du is going to be 2x dx. We do have the x and the dx, but the 2 is missing. So we'll multiply the integrand by 2 and compensate on the outside of the integral by multiplying by 1/2. Now we have u cubed du, and so let's rewrite the integral in terms of u. That's going to be 1/2 times the integral of u cubed du. But we're going to do one more thing. Rather than using these endpoints of integration, which we cannot do while our variable is in terms of u, let's convert these endpoints of integration into ones that we can use with our integrand in terms of u. When x is 0, u will be 0 squared plus 1, which is 1. When x is 1, u will be 1 squared plus 1, which is 2. So now we can use the endpoints of integration 1 to 2. Those are the ones that are suitable for the integrand in terms of u. Integrating here gives us 1/2 times 1/4 u to the 4th, which is 1/8 u to the 4th, and now that's going to be from 1 to 2. Let's plug in our endpoints of integration, first 2 and then 1. So this is going to be 1/8. We'll have 2 to the 4th minus 1 to the 4th, which is 1/8 times 15, 15/8. Now let's demonstrate that we would have gotten the same answer if we had converted this integral back to 1 in terms of x. So at this point, let's say that we have 1/8 x squared plus 1 to the 4th power, and then of course using our original endpoints of integration from 0 to 1. That's going to be 1/8 times 1 squared plus 1 to the 4th, and then minus 0 squared plus 1 to the 4th, which gives 1/8 times 2 to the 4th is 16, and of course minus 1 to the 4th minus 1, which also results in 15/8, the same result. That's it for today's lecture. I've always liked the amplified version of these verses. Can you find out the deep things of God? Or can you, by searching, find out the limits of the Almighty, explore His depths, ascend to His heights, extend to His breadths, and comprehend His infinite perfection? His wisdom is as high as the heights of heaven. What can you do? It is deeper than Sheol, the place of the dead. What can you know? Longer in measure and scope is it than the earth, and broader than the sea. Job 11, 7 through 9. God bless you, boys and girls.